All right, this is section 10.3, parametric equations and calculus. So in the first slide, I think it tells us what we're going to do. We're going to find the slope. We're going to find arc length. And we're going to find the surface area revolving either around the x-axis or the y-axis. And we've got formulas for all of these. So that's a good deal. Now, I will admit, there's a lot of not only algebra, but there's a lot of trig involved in some of these problems. So it's just a lot. It's a lot of trig. Let's take a look. Slope and the tangent line. So here's the formulas we need to write down. Remember, parametric equations deal with time here. They're using t, or you could say slope. So if they give us two parametric equations, to find the slope, it's dy over dx. And the way we look at that is we take the derivative of y with respect to t, find that answer, and then take the derivative of x with respect to t and find that answer, and then divide the two. So this is really important to have written down. And it's theorem 10.7 in the book. All right, so I never know what to do with these palettes. They're all over. You can't see them, but I can. Okay, so it says find dy dx for this these parametric equations here. Remember, dy dx equals taking the derivative of y with respect to t, and then taking the derivative of x with respect to t. So let's start off here. There's x. So let's take the derivative of x with respect to t, and you just end up with cosine t. If you take the derivative of y with respect to t, you end up with negative sine t. So it's dy over dx, negative sine over cosine. And are they going to let me keep on going? And sure enough, sine over cosine is tangent. So this part is tangent, so we end up with negative tangent. That's not bad. Now, you can also take multiple derivatives for parametric equations. They're showing, I mean, just to show you what this represents taking the second derivative. So we took the first derivative already, and then we're going to take the second derivative with respect to t. That's all that says. And I mean, that's just, they're just letting you know that you could do this. You can do a second derivative using parametric equations also. And not only second, it says multiple derivatives and third derivative. And we will have to take the second derivative here in a little bit. So let's take a look at this. Wait, did I miss something? No. Prolate cycloid. I like the picture. Kind of cool. We have, it says crosses itself at point 0, 2. Find equations for both tangent lines at that point. So if you look, we need to find the equation for this tangent line where t equals pi over 2. And we need to find the equation for this tangent line where t equals negative pi over 2. Right? This is a negative slope. This is a positive slope. In other words, pi over 2 and negative pi over 2 are the slopes of those lines. Let's go to the next page. I could do it from here, but I think we better keep on going. So dy dx, finding the slopes, dy dx. First, we take the derivative of y with respect to t. I think we need to go back and do that in the other page. We'll come back if it lets me. Come on, there we go. All right, so let's take the derivative of x with respect to t, and you end up with 2 minus derivative of sine is
cosine?
Yeah. Here, take the derivative of y. Derivative of 2 is 0. The derivative of cosine is negative sine. So this becomes pi over sine t. Okay, so we have our two derivatives. Now we can go to the next page, and I'm sure they have those there too. And don't forget, it's dy over dx. There's the dy, there's the dx. And we're plugging pi over 2 into these for one equation. We want to find a slope for one equation, and it's at time, pi over 2, but the other one is negative pi over 2. So let's just plug in pi over 2 first. I have pi, then sine pi over 2 minus pi cosine pi over 2. Let's break out your unit circle. I broke mine out somewhere. And sine of pi over 2 is 1. So this equals 1. So this is pi times 1, which is pi. And cosine of pi over 2 is 0. So this whole thing becomes 0, and we're just left with 2. So we're left with pi over 2. And by the way, we put pi over 2 in there. And so this is our slope. We ended up with a positive slope. If you put negative pi over 2 in there, you get the same thing, except you get a negative. So you get the same thing, except you get a negative. So this is our slope. One's a plus and one's a minus pi over 2. We have to plug it in they want us to write an equation. So we're going to use point slope. We have a point. Y minus y1 equals m times x minus x1. Y minus y1 is 2. The slope we got for this first one is pi over 2. X minus x1, and x1 is 0. So we end up with y minus 2 equals pi over 2 times x. And that's what we got here. And once again, if you put negative in there, this is what you would have got. If you just change that slope to a negative, this is what you would have got. And I think that's all they wanted. They just said, write the equation for those two lines, and these are the two equations. Arc length, another formula we have to write down. The square root of the derivative of x with respect to 2 squared, the derivative of y would with respect to t squared. So this is the formula for arc length. And you could write it like this: the derivative of the f of x equals the first function, and the g of x equals the second function. So let's just keep this formula here written down. You definitely need this. I mean, it's probably easier to write this down so you understand it. You're taking the derivative with respect to t. And so let's check out what the arc length would be. Now, if a circle rolls along a line, so there's a little story here, a point on its circumference will trace a path called a cycloid. If the circle rolls upon the circumference of another circle, the path of the point is called an epicycloid. And what they're saying is we want to find the arc length of the epicyclone. This you see there's a circle, you put a dot there, and as you're rolling it, this dot keeps on rolling around and form this beautiful flower. Here are our two parametric equations. And if you remember the formula, you have to take the derivative of each. So let's start off by taking the derivative of x. Derivative of x is -5 sine t. Derivative of cosine, the derivative of cosine 5t is, and cosine is negative, and then the derivative of cosine is negative. There should be a 5 in front because it's cosine of u, and du is just 5. So 5 cosine 5t. Oh, the derivative of cosine, I still wrote it down wrong. The derivative of cosine is sine. So this would be 5 sine 5t. And when you take the derivative of cosine and get sine, it's a negative. So this becomes negative, negative, and it becomes a positive. So I'm going to just erase that and change it to a positive. Here, derivative of y equals 5 cosine t. Derivative of sine is negative. You got u is 5t, so du equals 5, -5 cosine 5t. All right, so we have x prime and y prime. We're going to plug those into the formula. So I'll give you a second. And we'll go to the next page and plug it into the formula. I will say there's a lot of trig involved in this problem. I wasn't happy because I tried it with my paper. And, it was crazy. Now they are going to tell you this. So this is I'm glad they mentioned this. It says by applying theorem 10.8, that's the arc length formula. It says that the curve has sharp points at t0 and pi over 2. Sharp points, if you remember, sharp points, you can't take derivatives at sharp points. If you remember that from Cal 1. So what they're going to do is take the derivative between, instead of 0 and 2 pi, we're going to take the derivative between 0 and pi over 2. and multiply it by 4. And I'm going to go back to that picture, or I think they might go to the next picture and do that. Let me see. No, they don't. But we're going to take the derivative between 0 and pi. We're going to take this, and then we're going to find this arc length, and then we're going to multiply it by 4. Do you see? 1, 2, 3, 4. So we're only finding one arc length, because in reality, you can't take a derivative at a sharp turning point like that. You're not allowed to take derivatives of that. All right, so that's what they do. And so once again, here's the formula, but we're going to multiply it by 4. So we're going from 0 to 2 pi, 0 to pi over 2, and then multiply it by 4, and it'll go all the way around. It tells the arc length of all the way around. Okay, so. All right, so this is what we got for dx, I hope. This is what we got for dy. And they're square, each one is squared. Now, the rest of this, wow, that's, the rest of this is a mess. It took me several pages of writing this all down. You have to go in here, and I'm not going to do it, but you have to go -5 sine t plus 5 sine 5t, right? And if you square that, you have to write it twice and use FOIL and multiply it. This pen is just not letting me write perfect. Plus 5 sine 5t. And then you got to do the same thing for this. This is just this one right here. And then multiply this out. Distribute. And you'll notice there'll be some terms that end up canceling out. Actually, I think there's like 4 terms, 2 in here and 2 in here, that will cancel out. What happens is, I should have, when you get it, each one will have a 25 in it. When you multiply it out, you can take a look at it when you do it. Each one will have a 25 in it. So they factor a 25 out, and the square root of 25 is 5. So they bring a 5 out after they multiply it out. So the 5 times 4 is 20. That's how we got a 20 here. They factored that 25 out. You know, here -5 times 5 is -25. Each term in here that's left over will have a 25 in it. So that's how we factor a 5 out of there. The square root of 25 is 5. And then they give us some other clues for trig, how to get from whatever we had here to here. But then they say, okay, now that you have this, look at your trig formula sheet and look at the difference formula for cosine. And this converts to that. And then look at the double angle formula for cosine, or just the double angle formula, and this will convert to that. So there's a lot of trig there, and it's more than you think. It looks like it's a simple little thing here. It's not. There's a lot of trig involved there. And then when we're left with this, once again, the square root of 4 is just 2, and then the square root of sine 2t squared is just sine 2t. I think they're going to show us that. I'm sure they do, yeah. And so we said it was 4, we got that out, and then we integrated this. Remember, when you integrate this, you have to have a du since u is 2t. du is 2. So if I add a 2 out here for the du, I have to add a 1/2. 40 divided by 2 is 20. And then integrating sign, you get a negative. And then you plug pi over 2 into it, and then you plug 0 into it, because we're integrating from 0 to pi over 2. And that's what we got. And then there's a little thing in here that says, hey, you can take a look, and if you just look at the circumference of the circle, if you look at the circumference of a circle right here, they should be about the same. You see, the one circumference we got from that circle is 37.7. So it's an approximation. Once again, it's an approximation, and we got 40, so it matches up pretty good. That trig work in that problem, I wouldn't spend a lot of time on that trig work. I will not put a problem in there with all that trig work in there. There might be a little, but not. I mean, there's a lot of trig in that particular problem. Next, the surface area of revolution. 2 more formulas we have to write down. And you will need all of these. There's that test 5 quiz. It's not test 5. We don't have a test 5, but it's a quiz over chapter 10. And pretty much one of each of these questions will be on that quiz from this section. One of each of those questions will be on here. So the formula for area of a surface area is, if you look, it's really similar to the arc length. We just put a 2 pi in front of it and a function in front of it. If we're going about the y-axis, we put, if we're going about the x-axis, I'm sorry, we put the y function in front of it. If we're going about the y-axis, we put the x function in front of it. So it's very similar to the arc length with the function in front of it, and then don't forget the 2 pi since we're rotating it. All right, so let's take a look at this. And they're just explaining, hey, this formula is really similar to the arc length. All right, so let C be the arc of the circle, x squared plus y squared equals 9. Here's what we're going to be doing. Revolving about the x-axis. This thing is going to be revolving around the x-axis. And they give us coordinates, this coordinate, and they gave us this coordinate. All right. And let's see, they talk about you can represent C parametrically by these equations. And if you want to remember how to do that, go back to the last section, creating parametric equations and stuff. X equals 3 cosine t, y equals 3 sine t. We're going to take the derivative of each of those. Isn't that negative? Yeah. And this. And if you notice, here's the x. We put the negative 3 sine t, square it here. 3 cosine, square it here. We're revolving around the x-axis. So we put the y function in front, 3 sine t in front. And we're going from 0 to pi over 3. Don't forget about the 2 pi in front. And then there's just a little trig in algebra. I mean, this trig, this is a, by the way, this is a very common, this is very common problem right here. And you'll see it's actually an easy trig function. It's really common. I looked at this one and then I looked at one in the homework that's very similar. So if I was going to put one on a test or something, and I think I would pick this since the trig is a lot easier. So let's show you what's happening down here. -3, we're squaring -3, which is 9. 9, 3 sine square t, and we're squaring 3 here. We get 9 cosine square t. We're going to factor out the 9. You see the 9 factors out of each. The square root of 9 is 3, so the 3 pops out of there. And you can put the 3 out here. 3 times 2 is 6. So you're taking as much out as you can when you can those numbers. It makes it so much easier. Oh, I forgot to show one more thing. How did we get from that last line to this? And it's really a simple trig function. So, except I'm just running out of room down here. Okay. If you look right here, sine square t plus cosine square t, what does that equal? This is a standard trig function everybody should know and say, hey, yeah, I know what that equals. It equals 1. Sine square x plus cosine square x equals 1. So that's how we ended up with 1. The 3 came out. So 1 times sine t is what we're left with. So just remember, you're going to factor as much out as you can. You'll see one of these in a homework. If you have sine square t or sine square x, it doesn't matter. Sine square t plus cosine square t, that equals 1. That's on your trig formula sheet. And this is what we're left with. And then we're going to integrate 3 sine t, and when you integrate sine, it goes to cosine and you end up with a negative. So when you integrate that, that becomes a negative cosine. The negative came out in front. And the 3 times 6 is 18. Then you just plug pi over 3 and 0 into it. And this is what you get. I think that's it then. I think they wanted us to put the answer, oh no, in a decimal. I guess not. Negative 18 pi times a negative 1/2. 1/2 minus 1 is a negative 1/2. So negative 18 times a negative 1/2 is a positive 9, and then we have pi. So that's the finding the surface area when you're revolving it around a certain axis. And once again, you got to have those 2 formulas. You got to have all the formulas written down in this section, just so you don't forget them. I'd hate to be on a test and not remember the formula. And there's just too many formulas to try to memorize. All right, so that was that. Let me go to the homework now and just do a couple. There's I think 9 problems in this homework section. And some of them were a little more difficult than the others. I don't think there's any as difficult as that one trig function where you had to switch it using different trig identities. So here it just says, find dy dx. And once again, you have to have those formulas in front of you. Dy dx is in parametric is take the dy with respect to t, then take the derivative of x with respect to t. Here, taking the derivative of x, you get 2t. Derivative of y here, I get, that's 0, so that's just -2. -2 for y, and 2t for x. So this becomes -2, the top. The bottom becomes, what do we say, -2x, or negative, sorry, I said x, but it's -2t, that's a t. -2t, -2's cancel, so we're left with 1 over, wait, am I missing something? The bottom didn't have, the bottom, this didn't have a negative. I thought it was a negative, that's an equal sign. That bottom did not have a negative, so this is a -1 over t. And that's it, find dy dx, that's the answer. Number 2, I'm going to do number 1, number 2. I think I had 2 more on my list I was going to do. Number 1, number 2, 6, and 8. So number 2, find dy dx. So that's what we're going to find first. Once again, dy dx. Find the derivative of y with respect to t. Find the derivative of x with respect to t. We'll put them up here. X equals 4t. The derivative of x is 4. Y equals 7t minus 7. The derivative of y equals 7. So this becomes 7 on top, the derivative of y, and 4 on the bottom. Now, taking the second derivative with respect to t, this is what we got, 7 over 4. What's the derivative of 7 over 4?
0.
Yeah, any constant. It's a constant. Any constant, the derivative is 0. So we already know the first derivative is the slope. So this is the slope. What was the question? Find the slope. Yeah, that's the slope. And then determine whether it's concave up or concave down. If you remember that in calculus 2, not calculus 2, calculus 1, determining if something's concave up or concave down. So we already said our slope was 7 over 4. How do you determine if something's concave up or concave down? Does anybody remember that from Cal 1? Something about the second derivative is positive or the second derivative is negative, determines whether it's concave. Nobody remembers anything like that? Well, what's good about this, go ahead.
Are you talking about like with the graphs, like with the turns and concavity?
Yeah, you can look at the graph, but if you don't have the graph in front of you, you can take the second derivative at a point and determine if something's concave up or concave down, whether the second derivative is positive or negative at certain points. But that's why I just wanted to show you, that's why we took the second derivative here. We want to know what the concavity is. But if the second derivative is 0, that means it's not concave up or down. And another way of looking at this, our slope is 7 over 4. And this is an equation for a line, right? Since our slope doesn't have a variable in it, it's always 7 over 4. So there's no concavity, you know, you're not concave up or concave line for a straight line. That's what this equation is. If there was a letter, a T in it, you know, then you might have a concave depending on the power or what the concavity is at any given time. You know, this is concave up, this is concave down, depending on if the second derivative is positive or negative. So there is no concavity for this problem. It's not concave up or down because this is a straight line. The slope is constant. And the slope is constant, it's a straight line. You don't have any concavity. All right. What else would I said? Number 6. Okay, find the arc length. And so we need the arc length formula. Once again, not too bad. Square root of the dx dt, then square it, plus dy dt, and square it. So here's x. The derivative of this is 1/2 t to the negative 1/2, which also can be written as 1/2 to the t to the 1/2, or it also can be written 1/2 square root of t. And then y is 4t minus 1. The derivative of this is just 4. We plug the 4 into here and this into there. There's, see, they actually skip that step, but no, they don't, but they square it ahead of time. So if you look at 1/2 square root of t and you square this, you square the 2 and you get 4, square root a square, and you just end up with the t. So that's how they got this. And then they squared the 4 here and they got 16. All right, I'm going to erase everything on the right here in a second. So now, I mean, there's just a lot of manipulation, a lot of algebra involved here. So we're left with 1/4t plus 16. And we want a common denominator. You know, this is all in square root. So we want one common denominator, 1/4t plus, if I multiply the 16 by 4t over 4t, I can do that. You're just multiplying it by 1. I end up with 16 is 64t over 4t. So now you can make one fraction. And you got 1 plus 64t over 4t. And we can, this whole thing is square root. If you take the square root of 4, you can see a 4 pops out of there. So there's a 4 outside of here for, oh, not a 4, sorry. Square root of 4, this square root of 4 is a 2. A 2 pops out of there. So right there. And we broke this apart. This was 1 plus 64t. And they broke it into 2 pieces, square root of t. They just took the square root and put it on the top and the bottom. And then they said u equals 64. No, these. Oh, down here they show you. This is a really big help. I'm going to show you down here. They show you what u is. This is a huge help. Right here. This is a square root of 1 plus 64t over square root of t, but they say u equals 8 square root of t, which is really good. So do you see, this is u squared. This is 1 squared, or a, you can even say a squared. And then if you look at the derivative of this, the derivative of this is the 1/2 comes down, and then it becomes a negative 1/2. So you end up with the derivative as 4 over the square root of t. That's where they get the square root of t. That's the du right there. Oh, and the 4, if you take that 4, I guess the 4, oh, the 4 is on the bottom also. Sorry. And that's where they multiply that by 4. So this is it. So you can look at a square plus a u square on your, this right here on your formula sheet, on your 100 integration formula sheet. And it looks like it's number 26. So use, I think it's number 26. That's the one I had circled there. If you look at this and say, oh, you integrate this using 26, this is what you end up with, where a equals 1 and u equals, what did we say u equals? Oh, we had it down here, 8 square root of t. So they ended up with this, and then they plugged the numbers in and they got this decimal. They said round it to 3 decimal places. So there, I mean, this wasn't as bad, I don't think. I mean, there's not a lot, there's no trig in this, but I mean, I would have had a hard time. When I first looked at this problem, I'm thinking, okay, I know I have to get this 4t over there, but I wasn't sure of how I was going to approach this until I saw this help. Oh, well, if u is 8 square root of t, then if I square that, I end up with 64t. And there, oh, that's u squared. And then this is a squared. So that wasn't an easy thought process. I don't know if I would have got it right away without this help. So it's just something to look at if you see something similar to that. And then I wanted to do one more problem, number 8. Find the area of a surface generated by revolving the curve about the given axis. And we're going to do the y-axis. So if we go to our formula, wherever that is, remember the formula was 2 pi integrating. Here we're going to go from 0 to pi over 2. And it was, since it's the y-axis, you have to put the x here. Well, let's just, you have to put the x there. I don't know. The x function there. I don't know how I have to go back to that formula and just to see how they wanted to write it. Give me a second. Yeah, they just said ft. And then the square root of the dy dt, dx dt added together. Squared, right? Dx and dx dt squared, same as the arc length, and dy dt squared. So this is the formula. We're going to plug in 6 minus cosine right here. We're going to square this 6 cosine theta squared plus 6 sine. Oh, wait, we have to take the derivative. We didn't take the derivatives. The derivative of this is negative 6 sine. They wrote it here. And the derivative of this is 6 cosine. So we're going to square those. This is the negative the x. Let me erase that because I have them in the wrong spots. So this is 6 times the negative sine theta squared plus 6. Oh wait, this is the 6 is squared, everything's squared. 6 squared cosine theta squared. And so this is what we end up with. 6 squared is 36. Once again, we're going to factor out the 36. You see how this is common. Factor out a 36, square root of 36 is 6. So we're taking a 6 out of here and putting it here. 2 times 6 is 12. And then we're just, when we factor that out, we're just left with the sine theta squared plus cosine theta squared, which equals 1. Our trig function, this equals 1. So that equals 1. So then once again, we're left with 6 cosine theta times 1. This whole thing was 1. And this is what we got. Then you just plug the 2 things in there, pi over 2 minus, and then put a 0 in there. And that's what you end up with. So you see, once you try a few, especially this pattern here, sine squared plus cosine squared equals 1, things will factor out of there. And then you're just left with this, since that equals 1. Don't forget that 6 has to come out here. And that is 8.3. A second here. All right, I hit stop recording.